sir. Oh. You don't care now.
Okay, I'm gonna go over DFAs and regular languages, and then I'll move into proving whether a language can be regular or not.
Right.
Now, a lot of this is going to be rushed because there's a lot of notation that you need to know. So while I'm explaining a lot of the topics, I will try and give definitions to things like what languages mean, what regular means, and what a DFA means.
Mm-hmm.
Maybe not so this much because I'm going to go through the definition of what a DFA is right now. So at its core, syntactically, a DFA-N, so a DFA-N is defined as M is equal to a set of states, an alphabet, I'll go into what that means soon, starting state, a finishing state, and a transition function. Q is equal to set of states. The alphabet is essentially a set of symbols. A set of symbols that are processed by this DFA.
Mm-hmm.
Right. Once I show it visually, it'll probably give you a better idea.
Wait, can I briefly pause the lecture to see bit?
Yeah, it's okay.
I'll be quick. Sorry.
Okay, Wenchi, this is all you're gonna have to understand everything. Right, I'm gonna examine you tomorrow on it.
Oh,
You're gonna be doing the same exam that I did today. Okay, so Q0 is equal to the starting state.
That's a starting state.
I'll get into it very soon. F is equal to set of finishing states. And finally, the delta, and it's a function, is the transition function, which takes in a state and a value from our alphabet, and it returns a state. Right?
No,
Now-
you lost me.
Hmm?
You lost me.
Just wait. If I were to draw a DFA, I think it'll give you a better idea because
What's a DFA long form?
it's a DFA is something called a model of computation, right? If you think of a programming language, right, you're gonna think of the syntax behind it, right? And that makes sense, right? Because that's how you interact with programming languages. But think of say Python, Java, JavaScript, or any programming language you know, right? All of those have a specific syntax, right? But in the background, if you think semantically what they do, it's the same thing, right? You can write an equivalent for loop in Python, JavaScript, Java, C++, C#, and like any programming language, right?
Yeah.
So the whole idea of this module is to mathematically define what that semantic is, right? So think of all programming languages, it tries to unify them using maths,
Okay.
using rigorous mathematical definitions, right? And those things are called models of computation, right? And the model of computation, when I talk about, say, programming languages, is something called the Turing machine, right? It's called a Turing machine, and it's a lot more advanced than something called advanced than what the DFA is, right? And the reason I'm talking about DFAs is because they're the simplest form of these models of computation. So they're very easy to work with, they're very easy to understand, but they're not as powerful as Turing machines. They come under Turing machines.
I see.
And notice how I draw like dots here, which implies that there's things
They're
in
very
between,
different, yeah.
right? Yeah, there's hierarchies beyond it. So you start off with something very elementary, something very simple, and then you get something, say, I'll put on examples, you don't need to know what they are. If you get something called NFAs, get epsilon NFAs, right? They come a bit higher, then you get CFGs, which are context-free grammars, and you get something called PDAs.
Public.
Push down. Yeah, public displays. Push down automata.
Question.
Yes.
So can I clarify? So all the TM to DFA, like the whole like set of groups, they are all like different models trying to understand the semantic language.
Yes. The different models of computation. So the way a lot of these are represented, DFAs, NFAs, epsilon NFAs, and PDAs, they're represented using graphs, and you can think of that kind of makes sense, right? Because you can think of a program as a flow of instructions. You go from one state to another, right? So yeah, so they essentially think of a really high-level way of thinking about it would be to think of them as programming languages, right? Representations of programming languages that actually, I'm a lecturer. I need to be professional.
Oh,
Sorry.
wow, I'm so professional.
I'm sorry.
After lecture though, say something. But yeah, so you can think of them as programming languages, right? That have limited capabilities, right? The Turing machines are as powerful as any modern programming languages like Java or JavaScript or Python, right? These ones, they fall short of the power of TMs, that's why they come under it. They can't perform, they can't represent, if I'm using correct terminology, the same types of languages that TMs can, right? They actually represent, say something like DFAs, anything under, they represent a subset of languages that TMs can, right? So, moving on, this is a bit of a tangent about what all of this is. We're looking at DFAs, which are the simplest form of this mode of computation, right? So a programming language which can be written which represents the most simple form of computation, right? And if I were to break down the definition of a DFA, it is a discrete, finite automata. That's what it stands for. And the main idea is that it is finite, and it's something called an automata.
Yeah.
And it's discrete in the sense that we don't work with continuous values, right? It's kind of cool. And yeah, this is how it's defined. If I were to draw one, for example, I'd end up having this thing. These circles represent states. The arrows represents things going, the states that you move from the transition functions. And each state will read off a value, right, from your alphabet. And it will lead you to another state. So this is kind of what it's representing. So it's taking in the current state as a value, paired with the value that you're going to read, and it'll give you a new state. Right? Does that make sense so far? It's a bit of an abstract idea. Yes? No?
So like state comes in, get changed, then you
Think of it, you're kind of hopping between state to state, right? So
what's a state?
a state is this. It's quite literally the node that you're on.
It's a circle.
It's a circle, yeah. So
But, what?
I think that's probably the best way to think of it, like just as a circle. Now, don't think about what it represents, just think of it as a circle.
yeah, a lot of this is like say like a structure, right? And then you can use this structure to represent different types of computation. I mean, at the end of the day, like a programming language is just a bunch of text, right?
Yeah.
But it's like the combination of that text which represents computation. This is exactly the same thing, and hence it's a model of computation.
That's great lecture. Oh, wow.
So if I have this set of my alphabet, the signal I'll call my alphabet, right? Let's say it only has 2 letters in it, right? I'm just going to draw this entire DFA out, right? And I'll try and use this one as an example. So, what can I do? And as I'm drawing it, try and come up with, say patterns you recognize for what this represents, and see what actually makes up a DFA. By the way, I got this wrong. I just realized it's not discrete, it's deterministic. Deterministic, yeah, I completely forgot it was deterministic. And deterministic literally means that at any state, you know where you're going to go next. You're never guessing at a state, or you're never at a state and you don't have anywhere else to go, if that makes sense. But yeah, let's say this goes to another state, and if I read, say, A over here will loop back to this and okay, nice. Just a bit of notation. When I do this a transition, it basically means either A or B.
The
Right?
circle is the finishing state, right?
Yeah. This represents the finishing state, right? So this is what F is going to be in. Make sure that the fact that F is a set of finishing states, so I don't necessarily need to have one. I could have multiple, but I've chosen to keep one here for simplicity. This would be my Q0, so I'll put Q0 over here. Right? This is one of my finishing states. This is, all of these circles would come under my Q, my set of states over here. The alphabet I have defined. It's usually going to be something that's defined at the start. And your transition function, I mean, it does look a bit complicated, but the whole idea is, like I said at the start, you have the state you're at, right, and you pick a path, right. The word that I'm talking about here basically means pick a path. It can be either A or B, and that will lead you to a new state. So that's essentially what's happening, right. So if I start at Q0 and I decide to pick A, then I get to a new state. Likewise, if I start at Q0, start at B. Pick B, I get to this state, and at this state, this again is notation for A or B, right? I don't want to write, let's say, two transitions, which are like, parallel with each other, so I just need to do this. And over here, you see that it loops back. So, if I were to run every single word, right? Every single word, which is represented by this over here, right? And this basically means that it's going to be some word of size 1, right? Or in fact, actually, it will be something called the empty word, which is some word of size 0, take with the union of a word of size 1, size 2, size 3, and so on. So it's all the possible words you can make with just these two numbers.
So it's kind of like a power set.
Yeah, pretty much. The power set and yeah, so this basically represents any word you can make. And what you do with GFAs now, we're going to how you use them, is that you take every single word, so you take every single word and run it on this GFA, right? So if I were to take the word A, B, B, A, in fact, this is incomplete. If I were to do, say this, for example, yeah, I think it would be complete now. So, if I had to run this word A, B, B, A, I start at the start state, I pick the path which has A, so because there's an A in here, right? I read off the A, I take that respective transition into the state. I still have words I need to count, so I pick a B, right? I get over here, right? So this is done. I get a B again, right? But this time it's only going outwards and back in. So I read it, I'm still at the state, and if I read an A again, I'll return to the state.
Wait, so that is only a finishing state for A.
Sorry?
The finishing state thing, that's only for A's.
Yeah, okay. So you would say that this DFA only accepts, and by accepts I mean when you run a word on it, it will end up in a finishing state, right? It only accepts A's rather than B's. In fact, this is a pretty inefficient way of doing it because I could have just done an equivalent one, which does. Actually, wait, no. There's a distinction between the one I was about to do. Is it just? Okay, it contains just A's, right? Would it contain the empty word? The empty word is a thing which is technically part of this because we're running.
You mean contain or would it accept?
Would it accept? Accept is the correct word, sorry.
No.
Yeah, and why would that be?
Well, because it's not an A.
What?
It's not an A, so it doesn't get accepted by the A1 and then it just follows the rest of the thing until you get to the.
It actually doesn't follow anything.
Oh shit.
Like it just stays in,
Oh shit.
and Q0 is in the accepting state.
Oh.
So it was a lot simpler than that. But yeah, so this is an example of one word. If I were to do it for every single word, I get some words which would end up in these three states, right? And I'd get some words which end up here, right? So that kind of partitions this entire set in some sense.
Right.
And formally, we call the subset of this, which is accepted by this DFA. Huh?
Is this reg?
I mean, technically it is reg. No, okay. No, this definition isn't reg,
No reg.
but you're pretty much close to something to reg. It's actually the language of the DFA, right? So we define the language of M, the language of the DFA, to be the set, right, such that M accepts. Or actually no, it'd be the set of W part of the set such that M accepts W. Right? And this is the definition. This is how we define the language of M. Is there anything else I wanted to add?
The fact that you're doing this non-experts is kind of whack. Look at.
No, to be fair, this was like supposed to be the easiest one. And plus, I've taken out a lot of like the complexities because for every say this is mainly syntax, right? For every syntax that we wrote, we had to write like semantic definitions for it, and that involves making something called like a delta like dash delta prime function, which takes in a word entirely, and it's like a function which runs the word on the DFA, and then you define the language of M in that way. But honestly, I don't see the need of here because you've got the idea of what a language is right now, so it should be fine. But yeah, that's essentially what a DFA is, right? Now, I was talking about this hierarchy of models of computation, right? And this kind of links into what I mean by regular languages, in the sense that DFAs, they represent.
At the bottom. DFAs are at the bottom.
They're the simplest one.
That's LFAPS.
It's LFAPS. But yeah, DFAs, they represent types of languages, right? Each one of these, they represent a different type of language. And DFAs, they represent the simplest type of language, and you call it reg, right?
Oh, reg is if your thing can be represented by a DFA.
Yeah, that's essentially what a reg is. What regular languages are. So I think if I were to write that formally, reg would be a subset of the power set of all the possible words.
Wow.
Wait, no, that's wrong.
I'd just like to point out that you're making way more efficient usage of each chalkboard than I was.
Thank you. I tried. It's not my first lecture though. So it's some subset of. Is it the power set? No, power set would be a set of sets. So it's some subset of this.
Yeah, okay, that.
It would be an element of the power set of that. And yeah. So that essentially represents a list of words that we can filter out using a DFA, which is the simplest mode of computation, right? And in this sense, in this case, we've done so in this case, the language of M itself would be A, and it continues, right? But what about the language of all palindromes, for example, right? What about say the language which represents which writes out the Fibonacci sequence in binary, right? Like, is the DFA sufficient enough for it? To be honest, that was more of a rhetorical question.
I want to say yeah.
No, it's a no. Yeah, because look at this. This DFAs are deterministic, right? At each step, you need to know where you're going, right? So that's one of the key properties is deterministic. So at each state, right, I have an output from each state for every single element of the language. Oh, sorry, of the alphabet.
Yeah.
Right. If there was a C in here, then every single state would have to have an outgoing C. Some languages, right?
What's the other element in your sigma that just like isn't represented by anything in the DFA? So like you just add a C to that, and there's nothing on the DFA that has a C.
Then it's not DFA.
Oh shit. Okay.
Yeah. Because DFAs again have to be deterministic, and by deterministic it means that at each state, it needs to know. It has to have an outgoing value for each of the words.
So why
Right?
doesn't it just stay at the starting state then? Why doesn't it just stay at the starting state?
I mean, syntactically they're not really defined as that, right? Because the way it works is that, say if I were to put like a C over here, right? Actually, no, let's put like a C at the front.
Oh yeah, okay.
Then it doesn't know where to go, right? What you're talking about, actually, I don't think it comes under. Would it come under anything? Any of these? I don't know for sure. We actually haven't gone over that. But you could. It would definitely not be a DFA. Maybe it would be an NFA or any of the higher up ones. But by definition, I'm not sure, and I really don't think it would be the case.
Yeah.
But yeah, as I was saying, we have languages. We have different types of languages. Languages of palindromes, languages which are crazy, right? And they unfortunately cannot be defined by DFAs, right? And the whole point of this hierarchy, the reason for this hierarchy is because of the fact that you have all of these having the power to represent those languages, right? So the language of palindromes would be represented using CFGs and PDAs, right? If you wanted, say, a Fibonacci sequence, Turing machine would be your best bet. And the reason for that is that Turing machines are as powerful as any single programming language, and you can use a Python script to write, a program that generates a Fibonacci sequence. An interesting fact, there's actually, technically, it's not proven, right? But we don't know if there's anything above TMs. There could be something above TMs. And they have an interesting name, and they're called oracles.
Oh wow.
Which I found pretty interesting. But yeah, there's actually no proof whether TMs kind of encapsulate everything in this.
I mean, but like, if a Turing machine can run any piece of like code given enough time, like what goes above that?
I don't think you have a proof that it can necessarily do that.
Oh shit.
As far as I know, I don't think so.
No, because
PNP?
huh?
PNP is the thing, right? Or maybe.
I was just
I'm
gonna
just
say,
getting into it.
I thought halting problem was an example of something that a TM can't run.
Oh, actually, you are right. Yeah. Is Holt's TM recognizable though? There's two different types of TMs.
Oh shit.
This
This is out of my depth.
No. Isn't like you do have a point. I think the halting problem isn't recognizable either. If it isn't, then it lands that side, and you probably need an oracle to do that.
Yeah.
And I believe oracles require impossible physics. So,
Okay, cool.
we'll have to overcome that hurdle before we.
So then
get
doesn't
there.
that prove that there's nothing above a TM? It requires impossible physics.
I don't know. Like, this is all coming from, let's say, like 2 minutes of reading.
Listen, yeah, in 8 years when you're a prof, and that can be your PhD, not PhD.
Yeah.
It's like your.
I made an oracle guy. Cool. Okay, so we don't know what DFAs are. We don't know what regular languages are, and now we have now we know that like all languages cannot be regular. There's some languages that are too complex, right? So the next step is to think about, well, if I was given a language, how would I be able to determine whether a DFA for it is valid or not, right? How can I determine if it was regular or not? And I think that's a good question in the sense like for if you scale it up, right? If you're given any problem, there's no point in wasting your time on it if you know it's going to be impossible.
Mhm.
That was one of the things that I was told by my lecturer for this.
I mean, sometimes, well, I feel like for certain problems, like certain impossible problems, it's probably worth wasting your time, like the Riemann hypothesis.
Is it?
Probably.
As then, okay, but that's not guaranteed to be impossible. It's a conjecture. It could be possible. I'm saying for something, let's say sensible palindromes, if you were told to write a DFA for it, which you strictly cannot, right?
Why? Why?
Palindromes require you to know whether a string, right, A B B A, is the same when it's reversed, right?
Didn't you say that you could do that with 2 stacks?
Yeah, but DFA is
Oh,
the
yeah,
next
yeah,
stacks.
yeah.
And you actually only need one. 2 stacks are sufficient enough to be as powerful as a Turing machine. But considering the fact that palindromes come here, which only have 1 stack.
Okay.
But that's probably going to be another lecture. So, yeah, you have that, right?
Mm-hmm.
Now, as I was saying, you probably want some way to determine whether a language is regular or not regular. If you want to prove that it's regular, one way you could do it would be to just make a DFA for it. Right? One of the big relations is that if I should write this as a theorem. If language L is regular, then there exists DFA N such that the language of M is equal to L. And this is an if and only if relationship, so
Are you going to do the proof?
no.
No.
Because I'm going to prove something I personally think more interesting, in the sense that I could do pumping, but the proof for it is quite tedious and long. I can do a good application for it, and I actually don't remember the entire proof for it. I don't want to take on my lecture notes. But yeah, this is a property that all DFAs hold, and all regular languages hold. So yeah, if you were given a language and somebody was like, prove that it's regular, then it would suffice to create a DFA for it, right? But suppose you're trying and you can't find it, and you actually think it's impossible. How would we be able to determine that? And one of the ways is the pumping number. And I'd argue that it's the better way, but I'm going to go with something a bit more difficult, because why not? The Myhill-Nerodi theorem. And this states that the distinguishability relation on a language L, we should write that fully, if the distinguishability relation on language L, I'll define this soon, has infinite index. Do you know what I mean by infinite index?
No.
The equivalence class is infinitely long.
Oh, sure, okay.
So if it has an infinite index, then the language is non-regular, not. So we didn't exactly do the proper proof for this. It's more like a proofs idea. So we'll suppose this to be true, but we'll try and give it more reason by trying to understand why this property is the way it is. And the main idea is that this equivalence relation, what it does is that once you apply it to a language and you get all its equivalence classes, the cardinality of the equivalence classes, they give you insight about whether a DFA exists.
Can you define what the equivalence relation
Yes.
is?
So, if I have some X and a Y, and some language L, right? So X is indistinguishable from Y, if and only if, for all words, all possible words, XW, this is me concatenating the two words together. X could be any word, this could be any word. If I just join them together, is in the language if and only if YW is in the language. I hope I remember the proof for this because I learned it like last night. I read through it last night.
You got this, bro.
So yeah, this is the relation, right? And the whole idea is that if we have an infinite number of distinguishable elements or distinguishable words, then we can't have a regular language. And the key link to this, which I'm surprised we weren't told, is the fact that each equivalence class relates to a state in the DFA. And the number of equivalence classes are the minimum number of states you require to construct a DFA for a language. And it makes sense now that if it has an infinite index, then it requires infinite states, and thus it's not a DFA. And that's kind of the motivation behind this. And yeah, I'll try and prove it.
Wait, so are PDAs and CFGs, like, can they be possibly infinite then?
What do you mean by infinite?
Like, have infinite indexes?
No, DFAs can't.
No,
CFGs and PDAs, sorry. PDAs have a finite number of, all of them are finite automata.
oh shit.
But they have different amounts of, they have different levels of power.
Okay.
Right? And CFGs and PDAs, they kind of exhibit things you get from, let's say, a recursive language. I wrote a CFG today, which represents, like, which generates all possible, like, strings of predicate logic, for example, expressions of predicate logic. And the way it works is that you kind of have, if you have something that's recursive, if you have a string which is recursive, it can repeat itself within itself many times until you want to stop. Then a CFG is your best bet for it. And there's a proof that you do which shows that for every CFG, there's an equivalent PDA. For every PDA, there's an equivalent CFG. But moving back to this, you have this relation, which is used in the Michael-Nerodi theorem. And what I actually want to prove now is that the number of equivalence classes is the minimum number of states you require the equivalent DFA to have. And the whole idea relates around the fact, it's mainly using this definition, right? So, if I have, suppose, a DFA, if DFA n, right, has m states, we know that it's a DFA. I'm going to try and prove by contradiction. If it has m states, m states, and I have L to equal the language of the DFA, right? This language can now be used in this equivalence relation, right? And now suppose that, I think I'm writing this correctly. If I have this equivalence relation, right? Suppose its cardinality is finite, but it's equal to P, which is greater than N, right? Now we should be able to derive a contradiction, right? And if it has a greater equivalence class, right? Then in each of those equivalence classes, you have say, well, Q0, the starting state is going to be in some equivalence class, right? And then you're going to have Q, say, I'll do it with x's actually, x1, x2, all the way to x p minus 1. You're going to have all of these which are in different equivalence classes, right? If I have the function, if I have this function, right, which essentially takes in some word, right, actually wait, it takes in a state and a word and it returns the state. So it's essentially this transition function we saw, but using the entire word. So we can just plug the entire thing in and we get the finishing state. And yeah, you end up having that. Now, I think the idea is that if I were to run if I were to do Q0 x1 and then Q0 x2, right? I would have to have that all of these end up at different states. If that makes sense. Does that make sense?
Yeah.
Actually, wait, I don't think. Pretty
Let's
sure.
definitely go over it one more time.
So the whole idea is that it's really hard to it's pretty difficult to explain. These are all in different equivalence classes, and that means that if these are like starting points, right, in some DFA, if I have some DFA which has a starting value, x is like, it takes you some way halfway in the DFA, and then you have w which kind of finishes off to some state.
Okay.
Right. Basically, if this is the two words that are indistinguishable, if so these are two different words, so x and y. If their result for every single every single word you kind of add at the end of it, every single suffix, it leads to either an accepting state for both of them or a rejecting state for both of them, right? These represent words which you say you have something here, then there must exist some word which does something like this, right? So what that means is that these cannot actually be equal, right?
Yeah.
Actually, I think I might include Q0 because it does count as a valid example. Q0, and this is, I think, yeah, this would just lead you back to Q0. That makes sense. So Q0. So essentially, that means that all of these have to be different, right? Because if any of these were the same, right? If they were the same, say, state, then adding anything after that would lead you to a different state.
Yeah.
Right? And yeah, I think that almost just concludes it because of the fact that we've got m states over here. If we have p distinct states, then we've got a contradiction because, well, DFA m is already defined to have less states than p.
Is that how you draw your contradictions?
Yeah. Does that make sense?
Yeah.
So, yeah, because these, so to reiterate, because I think, well, because of the fact that all of these are in different equivalence classes, they cannot be equal, they must be distinct. They must lead to distinct states, actually. This should lead to some Q, this will lead to Q0, this will lead to, actually wait, there shouldn't be a Q0 actually here, there should be just X, yeah, just XP, because these are words. This should, some will lead to Q0, this will lead to, let's say, Q1, this will, let me do it this way. And if I go ahead, this will eventually lead to Q, N, right? But since, I think I'm getting a call, one second. I'll quickly finish this off, right? I'll get something like this, right? If I run every single one of these words, right, I'll end up getting states, right? Or finishing states, the states that they end up at. Now, since there's, actually, there should be, wait, yeah. And since there's a a p number of words, right? And then I have an n number of states. I must have somewhere in the middle that it ends up in the same state, right? But since all of these are different, right? Then, and also the fact that DFAs are deterministic, I kind of get a contradiction in the definition of what a DFA is. So I kind of get a contradiction in there somewhere. Because I'm pretty sure, so if two states are different and they end up in the same state, then it kind of contradicts the definition of what equals classes. Then they should end up at the same they ended up the same state. Then for any word afterwards, they would end up at the same conclusion. They'll either both get accepted or both get rejected, but that contradicts the definition of the significance class. And that kind of roughly concludes our proof. And that's what I wanted to do for this lecture today. Thanks for listening.
That was very, very interesting.
I hope it makes sense. Does it make sense?
Towards the end it got a little bit hard to follow, but other than that, everything.
Wait, I'll go over it like one last time slowly. Because I kind of did freestyle it. So you got this relation, right?
You're getting cool again.
Okay. That's enough.
You fell
One
asleep.
second, I'll be back. Hello.
Hard exam today. That's interesting. I've never heard anyone say something like that. Yo, let me stop the lecture before flipping. I lose all my storage.
40 minutes.